we can rewrite the variation of parameters formula in a useful way, especially if you're going to be reusing your work for other forcing functions. So the idea is that, let's see, we have, let's take the interior, so this is going to be y1 of x. On the interior, let's use a different variable, so we have y2 of t f of t dt w of t, and then we have y2 of x integral y1 of t f of t dt w of t. And so now I can put these inside. So combining these, we have the integral of, and let's see here, so I'm going to have y2 x y1 of t minus y1 x y2 of t, and that's all going to be over w, and I guess I'll need to make that a little bigger. Then I've got f of t dt. So the idea is to take this entire block right here. This is the Green's function for this problem. So the Green's function for the is going to be this y2x y1 t minus y1 x y2 t over w of t, and then our particular solution just looks like the integral of gxt against f of t dt. So what we have here, and so if there's an initial condition given at time x naught, this would be the integral from sorry, let's call it yeah, sorry, x naught up to x. There we go. And so it's interesting to notice that this whole thing in here, this is only data or information from the complementary solution. There's nothing about the forcing function. The forcing function only enters into it as the thing being integrated against. And so integrating against something, the term for this is just to say that this function of two variables is an integral kernel. And so just like a differential operator is a thing that you plug a function into and it spits something out, well, you might think, what if we could invert that just like a matrix? Well, that's exactly what's going on here. So this integral kernel G defines an integral operator. So what is an operator? Well, an operator is a thing that takes functions to functions. And a differential operator takes functions to functions by doing derivatives. An integral operator takes functions to functions by doing integration. And if you want to undo a differential operator, it stands to reason that you would want an integral operator, because integration and differentiation are inverse operations. Okay. And so the idea here is that if you apply L to G, then you should get something that looks like the identity. And for mysterious reasons, I will write it like this. Okay. Yeah, so let's look at an example. So suppose we have y double prime plus 16y equals some function, and I'm not going to tell you what it is yet. Well, you can still go ahead and solve this problem. So y1 is going to be cosine 4x, and y2 is going to be sine 4x. You can probably see that by inspection. If not, you can use the characteristic polynomial. Then the Wronskian is going to be, so let's see, so we'll have our cosine 4x minus sine 4x, sine 4x for cosine 4x, and this is going to be 4. So our green kernel is going to be, let's see, 1/4. That's our 1 over the Wronskian. And then we have cosine 4t sine 4x minus sine 4t cosine 4x, which after some trigonometric formula looks like 1/4 sine of 4 x minus t. And so then I know that the general solution to this equation is going to be c1 y1 plus c2 y2 plus my particular solution, which is going to be the integral of my green function against whatever forcing function you give me. So this is particularly useful, especially when you're doing something like trying to design a device, right? You engineers are always trying to design devices. Well, we will see that, for instance, if we're doing a mass spring oscillator, that this models something that has a mass of 1 and a spring constant of 16 and no coefficient of friction. And so you might want to know how that system is going to bounce around in response to a gentle shove. And so if you put in the a gentle shove right here, then you can use this formula to numerically calculate exactly what the output equation of motion is going to be.